So, in the last class we have looked at the velocity of sound, the Mach waves, how to define a Mach number, and we have also seen something called the stagnation quantities. Now, we will see how stagnation properties are related to Mach number. For that, we will start with the mass conservation. Aim is to write mass conservation in terms of Mach number. So, m dot is constant for 1D flow. Equals constant. We know P equals rho R T. So, I can substitute rho as P by R T. So, my m dot is now P by R T into area A into velocity V. I have defined my Mach number as velocity of the fluid by velocity of sound, which we now know as root of gamma R T, which is our A, as we have seen in our previous lectures. So, I substitute V as m into root of gamma R T. So, if I use this relation, my m dot is now P by R T into A into root of gamma R T, which is a constant, okay, or my P A root of gamma by R T is constant. So, this is another form of mass conservation equation. Okay. So, this is nothing but conservation equation. There is an m missing, Mach number m is here. Okay. Right. Okay. So, this is mass conservation in terms of Mach number. Now, let us look at our energy equation. Okay. So, in the TS diagram, heat input, heat transfer, okay, no shaft work, no losses. So, in this case, between process 1 to 2, my H1 plus V1 square by 2 plus Q equals H2 plus V2 square by 2 plus Ws. I strike off the quantities which are assumed 0. This is 0, this is 0. CPT 1 plus V1 square by 2 equals CPT2 plus V2 square by 2 for a perfect gas. I also know that my Cp is gamma r by gamma minus 1. So, I substitute that in this equation, the energy equation. So, it is gamma r by gamma minus 1 into T1 plus V1 square by 2 equals Cp gamma r by gamma minus 1 into T2 plus V2 square by 2. If state 2 is the stagnation state, what do I mean by that? I have taken the state 1 to a location where my velocity is now 0, and I have done this, assumed these 3, which means I have taken the fluid from state 1 which has some velocity to a location where the velocity is 0 isentropically with no heat and no shaft work. Thus, as 2 is stagnation point, which means this is my 0 condition. So, if 2 is the stagnation, then I can replace the equation as this T1 by gamma minus 1 plus V1 square by 2 equals gamma r 0 by gamma minus 1 plus 0, because now V2 is 0. So, gamma r T1 so I multiply this equation with gamma minus 1. V1 square is Mach number into gamma r T1, root of square of that. So, this would be V square is gamma r T1 m square divided by 2, and I multiply this with gamma minus 1. Okay, let it be here for the time being. Correct. So, I will rub this. So, I take gamma r T1 outside. So, this would be 1 by gamma minus 1 plus m1 square by 2 equals gamma r T0 by gamma minus 1, which I can rewrite as 1 by gamma minus 1 plus m1 square by 2 equals multiplied by gamma minus 1 equals T0 by T1, which is now d2 plus gamma minus 1 into m1 square gamma minus 1 equals T0 by T1. So, my T0 by T1 is nothing but 1 plus gamma minus 1 by 2 into m1 square. So, from process 1 to 2, if 2 is my stagnation quantity, then my static temperature and stagnation temperature is related to the Mach number at state 1 using this equation. Okay. So, likewise for any process there is an associated stagnation point, and if I know the Mach number at of the state, I can get the stagnation quantities using a stagnation temperature using this relation. So, for any process I remove the suffix. So, stagnation temperature is given by this relation. Now, this process is isentropic, which means my P0 by P is related to T0 by T as gamma by gamma minus 1, which is related to rho 0 by rho as 1 by gamma. So, if I know these ratios, I can get the other ratios from if I know the Mach number. Okay. Now, I go back to this equation which we have written a few minutes earlier. So, between process 1 to 2, between any process 1 to 2, so I have T S process 1 to 2, no heat, no Ws. There is some ds change. Okay. So, between process 1 to 2, if there is no heat and no shaft work, the stagnation enthalpy is same, which is what we have written here, and I can reduce it to this form, where now gamma or T1 is my A1 square by gamma minus 1 plus B1 square by 2 equals A2 square by gamma minus 1 plus V2 square by 2. So, if I know my sound velocity that is associated with state 1, then I have this relation. So, it is a kinetic energy of the velocity with the velocity, fluid velocity. This is the kinetic energy with the sound velocity, and you can equate that if the stagnation enthalpy is same. That happens when there is no heat, there is no work. Okay. So, the equations we learnt today, I will write it down here. It's already here. I would add it along with this A1 square by gamma minus 1 plus V1 square by 2 equals A2 square by gamma minus 1 plus V2 square by 2. Okay. So, there is a correction here, this is rho naught by rho to the power gamma. Okay. So, now to demonstrate the power of these equations, we will do a couple of problems. So, the first problem is I have a depth, location 1, my Mach number is 0.5, static temperature is 500 Kelvin, my static pressure is around 3 bar. Point 5. Okay. Mass flux. So, what is mass flux? Flux of any quantity is that quantity by area. So, mass flux is my mass flow rate by area. So, the equation we derived the early part of the lecture is m dot equals constant is m into p into a by root of gamma by r t. Which is constant. So, we use this equation to find your flux. So, it is a mere substitution. You know the Mach number, you know the pressure, A has gone that side. So, this would be root of gamma by r t. So, that is 0.5 into 3 into 10 power 5 root of 1.4 divided by 287 if I assume air. So, I assume air into 500 Kelvin. That would be your kg per second per meter square. Okay. So, it is a mere substitution of the equation which you have seen, but this is what you should understand. I have a constant area duct, I have a Mach number, static temperature and pressure. My mass flow rate is now related to these quantities. So, if I measure static properties or derive the static properties like this, I can get my mass flow rate. Now, the same question, if I have a different area. So, my area is now section 1 has 20 centimeters square, it says 40 centimeters square. So, I have m dot equals constant question may be to find your Mach number at section 2. So, you could relate your M1 P1 A1 into root of gamma by R T1 equals M2 P2 A2 divided by multiplied by gamma by R T2. So, if I know the area at two locations which is given, and if I know my m dot, which you have already obtained from this relation, if I use the same numbers there, then I can easily find my Mach number 2 if I know the T2. So, if I use the same numbers, so my M1 is 0.5, T1 is 500 Kelvin, P1 is 3 bar, then I find my m dot. I should find m2 if P2 is given, T2 is given. Okay. So, if my m2 is m dot by A2, which is given as 40 centimeters square. So, it is 40 into 10 power minus 4 divided by P2 or 287 T2 divided by 1.4. Okay, that would be your M2. I have a duct at some point here. I have m equals 0.5, P1 is 300 Kelvin, P1 is 3 bar. Okay. What is find stagnation pressure and stagnation temperature, which essentially means find T01 and P01. So, it is again a mere substitution. We take this relation T01 by T1 equals 1 plus gamma minus 1 by 2 into m1 square, which is 1 plus 1.4 minus 1 by 2 into 0.5 square. So, that would be your T01, which is how much? 315 Kelvin. So, P01 by P1 is 1 plus gamma minus 1 by 2 into m1 square to the power gamma by gamma minus 1, which is is 0.2 into 0.5 the whole square into 1.4 divided by 0.4 into static pressure is 3 bar. So, this would be 3 into 10 power 5 Newton per meter square millimeter square or 3.55 bar. Okay. So, if I reverse this question, the static temperature is 25 degrees Celsius and stagnation temperature is 250 degrees Celsius. Find the Mach number. How do we do this? I can use the same relation, 250 plus 273 divided by 25 plus 273 equals 1 plus gamma minus 1 by 2, which is 0.2 into m1 square So, your m1 square is now going to be something which is around 3.68 as per the calculation I have done. M1 is 1.92. So, if I know these two quantities, I can find the Mach number. Okay. So, in a sense, if if fluid is flowing from 1 to 2 and there is no heat, no shaft work, my stagnation temperature is going to remain same. So, if I draw that in my TS diagram, so in this case, so from state 1 to state 2, there is no heat transfer, no shaft work, which means my stagnation temperature is constant, my stagnation enthalpy is constant. So, for all the state that is associated with this, I will have the same T01. Now, if I can find my static temperature all along, I can find the Mach number variation all along my constant area duct. The measurement of static temperature is something which we will discuss later. Okay. So, that is the meaning of this question. So, put the question in a different way. If I have A1 to be a 340 meters per second, V1 to be 400 meters per second, and if I measure the velocity at section 2, it is 600 meters per second. So, what is my A2, what is my M2. So, it is again this relation. All these relations come from the energy equation, where we have assumed no heat, no heat transfer, no shaft work, and we have seen that then stagnation enthalpy is the same at any two sections. We use these relations, which is derived from those equation, which the equation is this. Everything comes from your combination of Reynolds transport equation with the second law of thermodynamics. Okay. So, everything has been reduced to this form from that. So, that is our parent equation. So, now this is another case where we can use that equation. There is no heat transfer, there is no shaft work. So, we could use this relation, where we know A1, where we know V1, where we also know V2. So, we can find A2. So, if you know A2, we can easily find Mach number V2 by A2. Now, we will end this discussion with a different form of this particular equation, which is now we are discussing. So, A1 is gamma P1 by rho 1 for an isentropic process, which we had seen. So, I substitute that here. So, my A1, I will rewrite that first. So, I substitute this equation. So, it is gamma P1 by rho 1 plus V1 square by V2 equals gamma by gamma minus 1 into P2 by rho 2 plus V2 square by 2. So, this relates your static quantities at section 1 and 2, which is originally derived from our integration of dP by rho plus d v square by 2 equals 0. From this equation, we have integrated and obtained this for an isentropic process, where P equals rho gamma equals constant. So, we obtained this equation, integration of this to that. Now, this is the same thing which we have obtained from this equation, where the stagnation enthalpy is same. We obtained this and this. So, they are all connected. So, if density is constant, and if it is you can reduce this equation to the Bernoulli's equation. Okay. Now, so there is a stagnation pressure associated with these two. So, I have state 1, state 2 undergoing whatever process we have written, no heat, no shaft work, and associated with 1 there is a stagnation state, there is a stagnation temperature, and at that point you also have a stagnation pressure. Likewise, you have state 2, associated with that there is a stagnation quantity. So, the stagnation temperature of 1 is same as stagnation temperature of 2, because there is no heat, no shaft work, but there is a P02 and there is, which is different from P01. Now, how do we evaluate these two? So, if I look at the Gibbs relation, my dH or TdS equals dH minus dP by rho. no heat, no shaft work. So, we have already seen dH is 0. So, your dH is 0. Now, ds should always be positive. So, to maintain this, the only way you can have is dP should be negative, which means my P02 should be always less than P01. Okay. So, this pressure P02 is always less than P01. With that small note, I will end this lecture, which essentially we have combined whatever we have learned in the previous lectures, the concept of stagnation, the Mach number relation, the sound velocity, all into the continuity equation, the momentum mass conservation equation and the energy equation. And we have done few problems to demonstrate the power of these equations. Okay. Thank you.